Hi everyone, my name is Harsha, and today I'm excited to present our work on efficient video playback optimization under device diversity and drift. This work is in joint collaboration with Pooya, Arash, and Mohammed from MIT and Zaheb from Prime Video. Large-scale video service providers deliver video to a diverse user base spanning heterogeneous devices and heterogeneous network conditions. They spend millions of dollars to tune their video delivery pipeline to enable good QoE for all users. We present a first large-scale study of tuning video playback system across these heterogeneous devices and network conditions and the challenges associated with it. But first, let me begin by giving an overview of video playback system. A video playback system consists of video player software and its interaction with video server and CDN. When we play a video on demand on our service, the video player fetches the manifest file, which describes the bitrate ladder, which is the set of quality levels the video is encoded at. Video player then picks a quality from this bitrate ladder depending upon its network state and current buffer, and requests it from the CDN. CDN serves this chunk, the player decodes and renders it, and the same loop runs for the duration of the entire video. This system has various tunable knobs. The first being the choice of ABR algorithm, whether it's a buffer-based algorithm or a rate-based algorithm or a hybrid, and the associated ABR parameters, such as how aggressive you want the ABR algorithm to be, its planning horizon, etc. Prior work has shown that ABR parameters need to be tuned for different networks to achieve optimal QoE. Other than ABR, video service provider also has various bitrate ladder design choices. Bitrate ladder design choice is dependent on the screen size of the devices as well as the video codec capabilities. Another parameter explored is the number of concurrent threads used to download the video chunks from the CDN. There are other tunable parameters in this system as well, but in the scope of this work, we focus on these three. To study the effect of video playback parameters across heterogeneous devices and networks, we conduct a large-scale study. We ran a randomized control trial across 750 million sessions over a period of 4 months. This RCT spans 84 treatments, where a treatment is defined as a configuration of the tunable knobs that we saw in the previous slide. And this RCT is run across a wide range of Prime Video customers, spanning 53 device models such as smart TVs, set-top boxes, etc., and 9 network clusters, which are defined by network bandwidth, latency, and predictability, and content types SD, HD, and UHD. This in total gives us a total of 250 cohorts, where a cohort is a group of users defined by the same network quality, device, and content quality. We estimate the QoE degradation for each treatment and for each cohort, and this heat map shows that. This QoE is a linear composite of 4 metrics: percentage of sessions with high rebuffering, percentage of sessions with high startup delay with frequent bitrate changes, and percentage of non-HD fragments delivered in an HD video. Next, we ask, is there a single treatment, is there a single video playback configuration that performs the best across all networks and devices? And in this plot, we show the best treatment per row with these white dots. And our first insight from this study is that the best treatment differs widely across cohorts, and there is no single treatment that will work across all your devices and all your networks. And hence, the goal of this work is to discover these best treatments so that we can maximize the QoE across all cohorts. But just observing that these cohorts have different treatments doesn't actually tell us much. The right question is, how much QoE do we leave on table by not picking the best one? That's why in this plot, I show the QoE degradation relative to the best treatment per row. And I really just want to emphasize here that in this RCT that we run, every one of the 84 treatments in our trial are production-grade configurations. None of these are toys or known bad configurations that will perform bad and give us high QoE improvements, right? And they are all configurations that we are willing to ship to users today. And even so, the gap is large. If we pick a treatment randomly from the set, we incur 30% more QoE degradation compared to picking the cohort's best. And if we tune at the network level, similar to how prior work has done, then, and what I mean by that is picking a single treatment that performs best on average across all cohorts in a single network, we are still 15% worse than the best. Tuning at device level improves These improves QE further, but going all the way to fine-grained tuning at device and network level closes the gap to 0. And for large-scale providers, these improvements are essential as the revenues are tightly tied to the QE of users. QE of users across all the cohorts. Now we have established from the data that tuning at device level improves QE. But let's try to understand it more intuitively why device level tuning is required. Devices such as desktop PC, gaming console, set-top box, etc., they vary in hardware, software, and management, which affects the video decoding time, packet processing rate, and available memory. Hence, the QE depends not only on the network, but it also depends on the device characteristics. For example, let's take the example of the download parallelism parameter that I talked about earlier. In this table, I show the percentage of sessions with rebuffering with one thread versus multiple concurrent threads. Some devices, such as device A and B, will naturally reduce sessions with rebuffering on increased parallelism. But some devices, which probably run single-threaded players, cannot easily benefit from multi-threaded parallelism. And here we see that device C and D have more rebuffering with increased download parallelism. This is an example of how device characteristics affect the right choice of configuration and why video playback treatments need to be tuned across devices. But this tuning does not come for free, and we'll see in the next slides that why per cohort tuning is expensive. For example, let's say we want to find the best treatment for a cohort row from the previous cohort configuration metrics that we saw. Data-driven configuration tuning methods like Bayesian optimization and bandits, they explore the full configuration space before converging to the best treatment. In this plot, we do Bayesian optimization for a cohort to discover the best treatment. And you can see that during exploration, Bayesian optimization picks treatments which incur a lot of QE degradation. And this QE degradation directly affects our customers' QE. Then there are two further challenges. For fine-grained cohort tuning, like at device and network level, this exploration will be done redundantly across cohorts, which would lead to high cumulative QE regret across cohorts. And another challenge is that video streaming QE is a heavy-tailed metric. Let me give an example. For example, on average, only 4% of sessions have rebuffering. So to compare two treatments, you need to accumulate a lot of sessions. And these fine-grained cohorts collect data at a lower traffic rate, which means to collect thousands of sessions, it's going to take a long time. And convergence, hence, can take from weeks to months. Hence, per cohort tuning is expensive for these two reasons: high cumulative QE regret and slow convergence. But do we need to do per cohort tuning from scratch for each of these cohorts? Don't you think there'll be any similarities across cohorts? Maybe similar devices will behave similarly across configurations, and similar network clusters would also have similar performance? Hence, we asked this question, and we performed singular value decomposition of this cohort configuration matrix. In this plot, I plot the cumulative power explained by the number of singular values, and we find that most of the cumulative variance of the matrix is explained by a few number of singular values, meaning that the matrix is approximately low rank. And the cohort heterogeneity can be explained by a few latents. Hence, we ask in this work, can we exploit similarities across cohorts to guide exploration exploitation, rather than doing it from scratch like how Bayesian optimization and multi-amp bandits methods do? This is how we came up with AGIM. To understand this better, let us use a production scenario. Let's say a new cohort arrives. Maybe it's a new device model that's arrived in the market, or the video service provider extending its service in a new country. And the goal is to find the best configuration for the cohort, right? And we just saw that the state-of-the-art methods like Bayesian optimization and bandits, they will explore the entire configuration space, which leads to high QE regressions. We present our system AGIM for efficient exploration exploitation. In AGIM, we use the data from already onboarded cohorts. We train a model which does few short predictions for this new cohort, and then use these predictions for efficient exploration and exploitation. And the two main design decisions of our system are efficient exploration by exploiting the similarities across cohorts, and as well as efficient exploitation by being robust to temporal drift and non-stationarities. Let's dig deeper into AGIM's design to see how we facilitate this efficient exploration exploitation. First, we either use historical RCT data, or we run a small RCT on already onboarded cohorts. When a new device arrives, we know nothing about it, and our goal is to find the best configuration for this device. We combine the RCT data collected with the new device row and kick off exploration. We start with a few bootstrap treatments. These give us some information about this new cohort and its behavior. The bootstrap treatments are chosen as treatments which are generally good across other cohorts. These measurements then feed into our prediction model, a lightweight neural network trained on this offline matrix and the bootstrap treatments. And we do a few short predictions using the QE of these bootstrap treatments and predict QE for all unexplored treatments. Now we can either stop here or we can explore the best of these predicted treatments. And finally, we recommend a set of K treatments that is recommended for this new cohort. This set of K treatments contains the optimal treatments, and this set is robust to non-stationarity. Let's go back to our previous Bayesian optimization example and see how AGIME performs on that example. In AGIME, the first phase is the bootstrap phase, where we do a small RCT on a few bootstrap treatments to estimate the QE on these bootstrap treatments. The second phase is guided exploration. We feed these bootstrap treatments as well as the historical RCT data from already onboarded cohorts to predict the QE for unexplored treatments. And then we use these predictions to guide our exploration and exploitation. We only explore the treatments that the model thinks will perform well, and that is the key idea in the prediction model. It captures similarities across cohorts. If a treatment performed poorly on cohorts that look the same as ours, the model will predict that it will perform poorly on our model too, on our cohort too. And AGIME simply never explores it. Hence, the high QE regret, which is common with Bayesian optimization during exploration, does not take place with AGIME, making our exploration efficient. The final step is the recommendation. AGIME doesn't pick a single best treatment. It rather outputs a set of K treatments, the top K performers of the ones that we just explored. This set is then handed off to a live adaptation system, typically a multi-arm bandit, and the multi-arm bandit will take these K candidates and dynamically assign a larger share of production traffic to whichever one is currently winning. But why output a set instead of the single best? That is because the best treatment drifts over time as the underlying system evolves. For example, there can be CDN updates or there could be firmware changes. And a single static best would go stale within weeks. And within a set, the multi-arm bandit can follow this drift, specifically a discounted multi-arm bandit which downweighs older observations, automatically tracks the current best as it shifts within our candidate set. And as I show in this plot, that while the treatment picked by Bayesian optimization achieves a low regret in January, its regret in February, which we compare with the best treatment in February, is a lot higher. And that is because of the non-stationarity. And picking a set of K treatments rather than a single treatment provides more robustness over non-stationarity. Comparing these plots with the AGIME's result, we see that AGIME achieves a much lower regret. However, this plot also shows a limitation of our current work, which is that the set of the treatments picked by AGIME can become stale over time. And hence, we need a continuous optimization system for updating the set of K treatments itself. We leave this for future work. To recap, AGIME's prediction and exploration phase picks candidate treatments, and the multi-arm bandit phase picks the live winner. Let me show some results. To evaluate AGIME, we emulate the new device onboarding by using the RCT data that I talked about earlier and leave one-out experiments. In this plot, I show the average exploration cost with number of explored treatments. As we converge to better and better treatments, the average exploration cost will go down for methods like Bayesian optimization and Pythias. Pythias here is the multi-arm bandit baseline. Versus AGIME actually doesn't require so much exploration. So even with very few number of explored treatments, it achieves high average exploration regret. And you can see in this plot that multi-arm bandit methods can actually get better exploration regret, but they are worse during exploitation. And while AGIME's recommended treatments, they are robust to the drift, I would also like to point out that Bayesian optimization and Pythias, they make worse recommendation with even 20 explored treatments versus what AGIME does with just 6 treatments, which is almost a 3x improvement in the convergence time. Now, most importantly, coming back to a live deployment case study in which we compare AGIME with the production treatment tuning service. This production treatment tuning service runs a multi-arm bandit over hand-picked treatments. These treatments are hand-picked by engineers who work in Prime Video and the research scientists who work in Prime Video. And we compared this with the recommended set of treatments by AGIM over 300 cohorts. And what we find is quite astonishing, actually. AGIM improved QE for more than 70% of the cohorts. On an average, it gains an improvement of 2.2%, and a more than 5% QE improvement on 17% of the cohorts. We also show the improvement in individual matrix here. Let me just show the explanation for each of these matrix. And what we see is that AGIM's treatments significantly reduce startup delay while avoiding major regressions on other matrix. To conclude, we show with our RCT study that device level tuning is critical, especially for large-scale video service providers who want to maximize QE across all heterogeneous devices. And we present our system AGIM, which does guided exploration exploitation, which exploits similarities across cohorts, hence minimizing the exploration regret, while being robust to non-stationarities. In our evaluation using RCT data, we show that AGIM outperforms Bayesian optimization and bandit methods, and significantly by a 3x faster convergence. And most importantly, we perform a live deployment comparing AGIM with production treatment tuning service and show a QE improvement of 2.2% on average and a more than 5% QE improvement on 17% of the cohorts. Thank you. I'll be happy to take questions.